Any questions? If not, then let's start the questions. Let me just right here. Brilliant. Okay, here. All right. See the screen. Okay. So the idea is comparing two quantities which both large or both small. I put the quote in small or large. Large means here is 50 and small being going to 0. So in our calculus, not in our old calculus, but in calculus, when you see 0, it's not necessarily it's 0 as a number, but it's really small numbers. And large means just that infinity. Okay, so the idea is this one here, like this one. So this limit. Or this limit. This is the case of the small, or both are large. Can be plus minus. Okay. So this is what I mean by comparing large quantities. In this case, this one, and comparing small quantities. Okay. So give you the example for this. Just this one here. Example. All right. So just take, this is x squared. Take g of x is just x to the 5, for example. Okay. So when you do comparison, x going to 0. Okay, so we have f on the top, this is the bottom, x to the 5th. So you by simplify this and you get 1 over x cubed, right? But 1 is constant, x cubed is small because x is small, then it is there. Okay, so what can we say in this case? In this case would be, well, if x going to 0, then x squared, f and g are small. But in this case, So what happened when you do comparison? Then it is large. Then that should be x to the fifth is much smaller than x squared. Or equivalently, you can say that x is much larger than x to the fifth. Okay, so that's the idea. But if you take the other way around, that means you take f of x is fifth, g of x is square. You switch the positions and you compute the limit. Okay, so let's simplify this one. X cubed. Well, limit is 0. Okay, so you see in this case, both are small. Okay, x to the fifth, x squared is small when x is small. Right? But you see that in this case, well, that's the same thing though. X fifth is much smaller than this one. So when you do this comparison, this limit, this 0, why? Because x to the fifth is much larger than, sorry, x to the fifth is much smaller than x squared. That's the reason why the comparison is 0, small. Okay. And sometimes you have this thing also. Say f of x is g of x is say and you make this comparison. So both are small when x are small. See? Well, you can cancel both and then we get a number. All right. So what our conclusion here is that you have a small over small is somehow unfair. Indeterminate. Well, sometimes it is 0, sometimes can be infinite, and sometimes can be any number you like. So this is the reason why we call it indeterminate. Okay. Now, similarly, you can say that you can take these limits going to infinity. Then it's going to be large. Okay. Say still f of x over g of x. Okay. So take from the first one. But now x is large. Okay, so x squared is even larger, x to the fifth larger. Okay, So then if you compute this one, of course, this is simplify. That's 0. Limit. Why? Because x to the 5th is large. 1 is constant. Okay, so this small. Okay. And similarly, yeah, so we have large over large can be anything from small, large, or any number. Okay. Okay, so our notations is this are called indeterminate form. Okay, so this is called the small over small. This one is large over large. So that means small over small is, we are uncertain. Okay, can be small, can be large, or can be anything. Similar with the large. Okay, so this is the main idea. So how we compute this one? Well, this is the thing we call Lobitovu. That so that means it has derivative. Oh, okay. Differentiable, and then let's see, then this limit prime. Let's see, let's see. Of that equals is 0. If this limit exists, and equals to L, then limit okay. So same thing with the okay, so both 0 over 0, small over small, or large over large. So instead of computing this directly, you compute this the derivative. So then this is what we call Lobitovu. So I won't prove this one. We'll use it. So example. Okay. So this is the thing that we know what to do. Okay. So just a note here. From the beginning that we know that this limit is hey, you remember this one? What is the limit for this one? What is the limit?
1.
One, right? Because that's a special trig limit. Okay, so let's compute this. This is one example of the when take the limit. This is 0/0 form. Okay, so in this case, let me just from the detail from the beginning. F of x, g of x. So is of the form small over small. Okay, and you see f g here is just a sine x polynomial, so both are differentiable. And you see that the f prime x is cosine x, g prime of x is just 1. So this limit is, let's see, what is this, cosine over 1. And this has limit now because just plug. Now this is the case of plugging in x equals 0 to this one. Let's get 1. And because this limit exists, then by Lobitovu rule, this limit is okay. So, but later on, you don't need to write down this the whole thing like this. So what you need to write is something like this. Out. So again, you're given the problem. Okay. You see, this is the form of, is this of the form uh, 0/0, small over small. Okay, so what you need to do here is computing this limit, the derivative. Sines become cosine. This is just 1. And this limit is 1. Because the limit exists, then you can use Lobitovu rule. Then it equals to this one by Lobitovu. Okay, let's do another example. Just get the the theorem A, L'Hopital rule of the form of type 0/0, and this holds also for infinity over infinity, so large over large. Okay, so let's take some. Okay. Okay, if you look at this one, let's check the form first. This is tangent, all right, so tangent going to 0. This is 0 over ln going to 0, so ln 1 is 0. Okay, so this is small over small. Okay, so we are going to use Lobitovu rule. So instead of this, we compute this one. So the derivative, tangent to x, tangent derivative of that's the what's the derivative of tangent? Derivative of tangent? It's secant square, right? So that's 2 secant square to x over ln is 1 over 1 plus x. Let's see, does it has limit? Okay, plug in 0, then it's 1. Secant 0 is okay, so 1 over cosine 1. So this is 2 over x is over 1. There. So the limit exists. Then by Lobitovu rule, this should be equal to this one. Okay, so the logic is you compute this first, and then because the limit exists, then this should be equal to this one. Okay, so this one comes later. After limit exists. After you compute limit. All right. Sin x minus x over x cubed. Okay. So this, let's check the form first. This is of the form, let's see, if you plug in 0, you get 0 over 0, right? So this is determinate form, okay? So therefore, we would like to use L'Hopital later, so we compute the derivative first. Derivative, let's see, sine become cosine. This is 1, 3x squared. Okay. And let's see. This one is still of the form, let's see, if you plug in 0, then this is still 0 over 0 form. Okay. Again, by using L'Hopital, because 0 over 0. Okay, and it's all derivative differentiable because it's polynomial and trig. Cosine negative sine x. This one sphere, and here we get 6x. All right. Now the limit exists, okay, because we know that's this is sine x over x. So this 1 over x. So this has limit. Okay, so either using special trig forms or use the other example number 1. Okay, so this is 1 over 6. All right. And because the limit exists, then this should equal to this one by Lobitovu. This one. And that means this limit exists. And that means this limit should exist too and equals to this one, the original. Okay. So the equal sign of the L'Hopital rule comes later after we compute the last limit. All right, so and it's common to use more than once the L'Hopital rule. Okay, let's do other example. All right, just from here, show you what's wrong with this one. Okay, let's check the example here. 1 minus cosine over x squared plus 3x. Okay, and let's check the what do this one is just let's take derivative. This becomes sine the 2x plus 3. Okay, and then just proceed again with the L'Hopital. Sine becomes cosine. This is 2, and this 1/2. But this is wrong. Why this is wrong? Because let's see. Let's see this one here. If you plug in 0 to this one, well, this is correct. But the second one, if you plug in 0, this is okay. While 0 over 3, this is not indeterminate form. Indeterminate. This is bad connections. It's slow. Okay. So what's wrong with that is that the first L'Hopital is correct, but this one is wrong. The second L'Hopital. Okay. So instead we finish with this one. So we compute this directly. This is 0. So instead of applying another L'Hopital rule. Okay, so you should check the form whether it is really indeterminate form. Okay. All right, and this is another example of, well, it is correct of using the L'Hopital rule, but it doesn't lead you to any answer. For example, this one, e to the negative x and x to the negative 1. All right, so if you compute, x is large. Okay, so this form is, if you compute, this was e to the, so this is 0 over 0. So it is legal to use a L'Hopital. Okay. So check this. So this e take derivatives. All right, so this is negative and this is negative, and the negative cancel. All right, so you get this. And if you compute the form here, you plug in, say, take limit infinity, and this is 0/0 again. And you attempt to use another Lobitovu rule, take derivative again. You have another negative sign, so this will cancel. Take derivative. But again, this is okay. And you can keep going on and on and on and on, and just make things worse, because you see, on the top numerator, you have e to the x always. But then the denominator, you have, this is 1/x, this is 1/x², this is 1/x³. All right, so you make the denominators get even worse, even more complicated. Okay. So clearly we are only complicating the problem. So what we need to do, here we just need to write down e to the x is just 1/e to the x. Right, so this 1/x, so you just put it on top. Okay, so if you take this limit, both numerator and denominator, this is of, so both are large. So this is large over large. Okay, so you can use now the Lobitovu rule. Is going to infinity, take derivative 1/e to the x. This is 1/large, so the limit is 0. So this justify us to use Lobitovu. Okay. Some more example. All right. So now our limits getting more complicated by using Lobitovu. All right. So let's see. Let's check this one now. Say problem 12. All right, so let's try to figure out what kind of indeterminate form is this one. Okay. See if you plug in 0. This is 7 power 0, this 1/1. So that's 0/0. Okay. So take derivative. All right, so just getting limit. When you take derivative, this is the same thing, except you have 1/ln 7. Okay. 1/ln, or sorry, What is derivative of one? Another 7. Sorry, plus. Okay, so times ln of 7, ln of 8, or just this one. The x is just a to the x ln of a. Okay, so now what we have here is that this is 7 to the square root of x, ln 7 times derivative of square root of x. Okay, so we have here 7 times derivative of this, we go change rule. 1/2, 1/2. Okay. Okay. And the denominator, sorry, 7, 2, ln of 2, 1 over. All right, so just cancel. And this limit, this has limit now, because this is going to be to 1. This ln 7, the limit is okay. So the limit exists. So then this justify using the Lobitovu. Okay, this ln 7 over ln 2. Okay, any questions? Questions? All right, one more example, 23. See, if you plug in 0, you can so the integral from 0 to 0, then that's 0. Okay, this going to 0. So this is all small over small. Okay, because small over small, we attempt to use a Lobitovu and take derivative. So we compute this one instead. Dx 1 over dt, and the dx is just 1. And recall that this is a fundamental theorem of calculus, saying that when you take derivative, then just cancel the derivative, cancel the integral. Okay, so what we have here is now is just substitute this one with x. Yeah. And now this has limit because this x going to 0, 1, 1, 15. So the limit of the ratio of derivatives exists. So by Lobitovu rule, then it should be equal to this, the origin. Okay. So then that's the example of some example of doing Lobitovu. All right, we'll take a break here and then continue with other indeterminate forms. Questions? All right, so let's take a break.